All right, Brian. Hey, welcome to this week's episode of Lost Origins. Man, we are so stoked that you took the time out of your day to join us to talk all things your background, your work, your theories, losing a Nobel Prize. I'm super excited to jump into that. But just thank you so much for hopping on with us today, man. This is going to be good.
Yeah, thanks, guys. Been a big fan of the work you guys do, and it's an honor to be on the show.
Oh, stop it. That's weird. We appreciate it.
I've been stalking you for years. And
That's cool. That's cool. So let's do this, man. One of the things that we always like to open the shows with is, for people who maybe have not encountered your work in the wild or whatnot, we always like to set the stage by giving you the opportunity to just hit us with a little bit of a history lesson, right? Who is Brian Keating? What is the focus of your work? Well, what brought you to this moment today? Just that 35,000 foot view. Why don't you break us off on some of that real quick?
Yeah, I'm going to give you the 14 billion light year view,
Yeah.
not just 35,000. 35,000 is so Earth-centric. What I do and what I've always been animated by is the same thing that drives you guys, which is the search for origins. And what that means for me really took on a twofold mission, in that I wanted to understand the deepest possible evidence that one could find for the origin of the universe. And I'd always been fascinated by that because it's really the only story. If you think about it, every other story from Sherlock Holmes, to some modern day story, hillbilly elegy. I don't know. You could think of any story, any nonfiction work.
Mhm.
It always starts in the middle of the story. It always starts in what's called in media res. But if the universe had a singular origin and what we normally think of as the Big Bang, then time itself didn't exist before that moment. And we now believe we think we can date that moment very accurately, and we'll get into that. And so I asked the question, of myself as a young kid, how would time possibly flow? How could time change if time had a beginning? And that really kind of impelled me to think about really the biggest questions that one could potentially answer. And thankfully, I say I haven't answered them because it gives me job security. These questions are very difficult to answer.
Sure.
And the second type of origin is I really wanted to understand my own origins and really what made me tick and how I came to be here on Earth, and both culturally, ethnically, however you want to say it, and as a scientist, and how that animates me to want to see and influence my worldview and my philosophy of life through the lens of being a scientist. And those two things animate me very deeply and drive me to do the work that I do. And the daily tasks that I engage in are really not those that I had aspired to do with these twin visions that I just described. So most of the day, I'm not sitting around stroking my non-existent beard, pondering the multiple universes in which we might inhabit. But instead, I'm doing mundane things like, signing a receipt for a travel form for some trip I took 3 months ago to San Jose. And, you're doing very mundane things. And I usually say that my job, so I'm a professor. I teach physics and astronomy at the University of California, San Diego. I've been here over 15 years. I can't believe it. And it's the most wonderful job in the world because it allows me to essentially get paid to do something I would do for free and did for free for many decades, which was try to look out through telescopes to see what the early universe looked like.
That's amazing. I love it. And what I'm hearing right now is like when you do what you love, right? When you're passionate about your craft, it makes it that much easier to get up and do the thing every single day and stay motivated and stay plugged in. The phrase, when you love what you do, it's not work. I don't agree with that at all. It's kind of the opposite in my mind, right? It's like, no, it's harder because you're that much more invested in continuing to fight the good fight. You know what I mean?
Right. Yeah, exactly. So I've heard that phrase slightly differently, do what you love, the money doesn't matter. And then if you only do what you love, you won't have any money to worry about. So be careful. You have to strike a balance between doing something that's practical. And I always joke, my deepest love is actually philosophy and trying to understand the meaning of existence and the essence of the search for truth and knowledge.
Yeah.
But I was bewildered by the overwhelming amount of job opportunities I'd have as a philosopher. So I never went in to become a professional philosopher. I'm just kidding about that. That would be great if philosophers, were as richly rewarded as shortstops in the
wouldn't
Major
that
League
be
Baseball.
the day, right? Shortstops and mumble rappers. We got got to we got to adjust some stuff here. So just like hit me with like what's the daily delta look like for you out of curiosity, right? Like you had mentioned, the mundane tasks, but like when you're in the throes of a project or you're working on trying to answer certain questions or work towards a goal with a team, like what kind of stuff are you working on? Give us a little bit of context for some of our listeners who maybe are not familiar with the role of an astrophysicist.
Yeah, so perhaps the most familiar job of an astrophysicist in a university setting, which is that of being a professor, namely a teacher, that's the most commonly and correctly so associated feature of a professor, someone who teaches and lectures and so. But that's a very small portion of my job. That's about 3 hours a week when teaching classes, 3 1 hour a week classes. The other, in my case, 57 hours a week is really spent as a small businessman, which is involving all sorts of different tasks from payroll of employees to travel to logistics. We're building the world's highest cosmological telescope in the high Andes Desert of northern Chile called the Atacama Desert. And this telescope is a $100 million class project. It's comprised of 260 people on all 7 continents. And I'm honored and blessed to be the director of this project. And that means, the bucks, 100 million of them stop with me. Not that I get to keep any one of them, but I have to, have the ultimate oversight on how that money is obtained and eventually dispersed. And I rely on the work of a huge team. I mean, you think about how big a business that has $100 million budget over, roughly 10 years. That's a decent sized small business. And with that many people distributed on all 7 continents, it's a logistical nightmare to really get all the vendors, all the subcontractors that were building this telescope at the world's highest altitude observatory of its kind. And we're trying to do something, not just, build a Starbucks at the top of a mountain. This observatory is the most exquisite and sensitive and advanced technologically of its kind. I'll give you one example.
Yeah, please.
We have devices called cryostats. So normal person looks through a telescope. You're using your eye as a detector, and the lenses that are in the telescope are the telescope itself. For us, we have lenses that the human eye can't see through because we're looking for heat, not light from the Big Bang. And our eyes are not the detectors. Instead, they're very exotic type form of material called a superconductor. And we don't have billions of pixels as we do in our eyes or in the largest optical cameras. We only quote unquote have tens of thousands. But each one of those has to be cooled down to 1/10 of a degree above what's known as absolute zero, the ultimate stopping point in temperature below which there exists no temperature. Just as perhaps before the Big Bang, there exists no time. And I hope you're thinking maybe right now there could be a connection between the absolute zero in temperature and the absolute zero in time. And maybe that's something cool we could talk about either today or next time. But
sure.
The ultimate thing that we do is we build ultra-sensitive technology and detectors. And to do that requires a tremendous amount of logistical support, design, and capability. And the greatest blessing that I have are the people that I work with. I work with the smartest 260 people in the world. I can really say that these are the most brilliant people. I learn from them every day. They range in age from 18 to 80.
Wow.
And they are some of the most accomplished men and women, as I said, from every continent on Earth, including Antarctica. So it's just a fascinating, that gives me great joy, and that I get to learn from so many people on a daily basis, even if I don't get to really ponder the universe's deepest, darkest secrets on an hourly basis.
Well, and you're still able to just like subject yourself and submerge yourself in amazing technology, right? Like how like for granted we take things on a daily basis in like the civilian world, quote unquote. Like I'm at Target the other day, just fascinated by the iRobot Roomba and how this thing's going to clean my living room for me without me being at the helm. And you're like playing with gadgets and technology that is just so next level. It's unbelievable. It's so cool. It's so cool.
Sometimes we have to invent the technology that's then used to do the astounding measurements that we're trying to do. So these are really at the forefront of human knowledge, and no single person can do all that. And by the way, it's not only building the technology that is as complicated as building, say, Apple's new building in Northern California.
Yeah,
there's just a technological aspect of it, maybe even harder. but it's the analysis of data, which is equivalent to, like thousands upon thousands of the biggest hard drives that we have every year.
Yeah.
And that data, we can't throw it away. Every single bit and byte of data is precious and must be mined, because that data originated from the most ferocious, explosive expansion of the universe 14 billion years ago.
Right.
And for us to not treat every piece of data, every photon, every particle that we detect, that would be a waste of this beautiful opportunity that we have, courtesy of the technology that we built.
Well said. Well said.
So, Brian, this is a pretty exciting month for you. Your book, Losing the Nobel Prize, celebrates its 1-year anniversary. And, there's some pretty amazing endorsements in here, right? Like Sir Roger Penrose, just huge hitters in the field. So, let's ditch the water wings, jump into the deep end. And can you explain, what's the focus of the title? Bring us into kind of behind the scenes. What inspired you to write Losing the Nobel Prize? And what can readers expect?
Well, I always had a love of books and a love of popular science in general. As a kid, I read a tremendous amount. Carl Sagan, Isaac Asimov, Jane Goodall, these titans of popular science communication. But I never thought I could really do it. And I really probably wouldn't have done it myself had it not been for the fact that I was an eyewitness to an event of such singular importance in the history of cosmology, that and that one that I played such a big role within, and that's the putative discovery of the spark that ignited the Big Bang that we observe today. And we claimed in 2014 that we had witnessed the explosive origin of the universe, a period of time known to physicists as inflation, which is a form of really mysterious energy that would have pervaded the extremely early universe. We're not talking about a billion years ago or 10 billion years ago. We're talking about 1/trillionth of a trillionth of a second after the Big Bang itself, after the origin of the universe.
So like immediately after the singularity, then? Is that kind of what we're looking at?
Perhaps, yes. Perhaps immediately after that singularity, about which we know almost nothing,
right?
Which made our discovery so exciting, because it would be the first experimental observation of data, of relic radiation from that early origin of the universe, and data that could be obtained by no other means. And so this was the BICEP 2 instrument. I had created what was called the BICEP 1 instrument, which the BICEP 2 instrument built upon, used the same design, the same optics, the same site at the bottom of the world at the South Pole, Antarctica. And it had been the predecessor for an upgrade called BICEP 2, which was the instrument that made headlines around the world with millions of people witnessing it, to really unravel what the universe might have looked like in its most early phase. And then that discovery had been told to me and to many other people, if accomplished, would result in a Nobel Prize. And so, spoiler alert, from the book, his title, you can determine that I did not win the Nobel Prize, in fact. But the Nobel Prize title, the Nobel Prize in the title, Losing the Nobel Prize, has a double meaning, which is that not only is the story a memoir of what it's like to aspire to win a Nobel Prize, to achieve the ultimate in humanity's accolades, but also that there are aspects of the Nobel Prize I came to discover later, both by being in the running for one, arguably, and also being asked to nominate the winners of the Nobel Prize the following year, those twin encounters really set me up for a voyage of discovery into what was the lost origin of the Nobel Prize itself. How did it come to be? What has it evolved into? And how is it affecting the way that science is done? And in turn, how does that affect scientists? So in short, I felt it was a book I could not write. I could not write. And it was a book only I could write, because I had played such a crucial role in the scientific encounter and also in the Nobel Prize, kind of run up and then denouement. And how my suggestions to reform the Nobel Prize have redounded, hopefully, to the benefit of the Nobel Prize itself. And only time will tell with that. So it's been a controversial book. It's been a popular book, a bestseller in terms of popular science books in astronomy. And as you mentioned, I was honored to get a tremendous number of blurbs from the most eminent scientists in the world. including Brian Greene and Sir Roger Penrose,
Sure.
Lord Martin Rees, David Spergel, and many other great scientists in America and abroad.
That's amazing. And holy hell, man, like you're the first person to ever organically work the title of our podcast into an explanation of your work in your book. So that was super cool. Thank you for doing that.
I like to do my homework.
I see what you did there, and I appreciate the hell out of that. So that's great. So that's cool. That's really cool. So like one thing that I found really interesting when I was digging up, information on the internet and just like the overall intent of the Nobel Prize, it basically seems that like the native purpose of this accolade has kind of been, I suppose, mutated over time, right? So like maybe explain for our listeners, like just the overall background of the Nobel Prize, who created it, why, and then maybe do you think that the original intent of the Nobel Prize is alive and well today? Just like maybe your thoughts on the beneficial or potential negative effects that the recognition holds within the scientific community as a whole.
Yeah, that's a great couple of questions.
Loaded question. Yeah, sorry.
Yeah, I mean, I realized that the Nobel Prize, I'd always been aware of it because there are so few people. I give this analogy. There's only been about 2 times as many people that have ever gone into space as are currently living Nobel Prize winners in physics. So it's this incredibly rare thing that if people have heard of, they know it's an incredible honor. They know it's like it signifies brilliance, unquestioned genius, but they don't really know much about how it began, what its purpose was, and what it really is doing to science and scientists today. And I make the analogy, it's kind of like the Oscars and the Emmys and the Grammys and, the Nickelodeon award, everything that could possibly be rolled into one for scientists. Mm-hmm. And it's only given out in 6 different categories, including physics, chemistry, medicine, and literature, peace. And then they added about 70 years after the first Nobel Prizes, this committee added a Nobel Prize in economics. And that has a lot of controversy associated with it.
Sure.
But I came to realize that the Nobel Prize had become almost sort of an idol that scientists themselves, who are predominantly atheist or agnostic at best, who certainly very few affirm actively belief in a higher power, that they were almost as guilty of worshiping this gilded graven image of Alfred Nobel, the patron saint, the creator of the Nobel Prizes, as any religious adherent would be for any religious iconography. And so it became kind of scary to me that so many of my colleagues and friends, including me, and I always admit I was the worst, the most afflicted by this disease, that I consider Nobelism, which is an obsession or affliction of wanting to win the Nobel Prize. And I started to analyze myself psychologically. Why was it so important to me? And I came to realize because of the sort of way that it's been elevated and the way that it's really kind of strayed from what Alfred Nobel originally intended, which was merely as a way. In 1901, the first Nobel Prizes were given away. And in physics, the first prize was given to William Röntgen, who discovered X-rays. So if I went back and looked at the Nobel Prize will that Alfred Nobel wrote in 1896, and this will was amazing because it really recorded what his intentions were for the very future of humanity, and that he wanted science, technology, literature, et cetera, to work for the benefit of mankind. And that the discoveries that were to be awarded by this prize were to be those that had an inclination towards peace or prosperity, but making human life better. So the very first one given for the X-ray, obviously that had tremendous benefits. Because it allowed people to see into their bodies and detect maladies and diagnoses and so forth. And that was clearly beneficial. Nowadays, we've strayed into the realm of really abstract science, which is, I would say on an abstract level is beneficial to the human mind. But on another level, it is quite far removed from what Alfred Nobel wanted. And so I asked myself, this man who had no children, no wife that we know about, he gave this money, all of his fortune, which would have made him, as rich as Steve Jobs or somebody is today. He gave this vast fortune, which he had accumulated from creating and patenting dynamite. And that fortune was meant to kind of reclaim his reputation and the Nobel name. And so it was a very small prize, very niche thing that's really taken over the world and become a multi-billion-dollar industry and very crucial to the fabric of science nowadays, even though it was really started by one guy. And even his original intentions have really been subsumed in what's now become of this prize that bears his name.
Walk us through that. I'm just curious. Do you think that like the crippling effect of the Nobel Prize is basically stemming from the fact that it's become a status symbol, or do you think that it's potentially the cash purse that's at play here? Like it's almost like the monetization of the space as a whole, just kind of the way our society looks at a thing, whether it's good or for profit, nonprofit, and it ends up being morphed into this like, well, how can we leverage this and utilize it to advance our initiative or increase our profitability or whatever, or maybe it's a combination of the two depending on the individual based on what motivates them. I don't know, like based on your experience, the conversations that you've had with other potential candidates who are up for the Nobel or just people within the circles that you run, have you had any conversations as to like what the systemic cause for this is?
Oh, yes. Yeah, definitely. I mean, I speculate on that in the book. I should say the book is mostly a memoir of what it's like to do science and an explanation of what modern cosmology knows about the mysterious ultra early evolution of the universe and how that impacts the potential future of the universe. But there are 3 chapters devoted to the Nobel Prize itself and what could be done to reform it. And really, the monetary benefit is relatively, not to sound, snobbish, but it's very small in that it could be split 3 ways among 3 people at most, which is not what Alfred Nobel wanted. He wanted it to go to 1 person. So they changed it later in life to make it 3 people. But I think that made things worse because, it's like if you're not the 1 person who gets it, well, you're in a really good, group of maybe 1,000 other people on your project who didn't win it. But if there's 3 people that won it, well, I really did more than that person. And so it really has created a lot of acrimony. And actually some studies suggest that a Nobel Prize is detrimental to collaboration because these collaborations dissolve after 1 person wins it or 3 people win it and the other 27 to 1,000, 48 people don't win it. But getting back to the actual impetus. So the money's $1 million split 3 ways. If you live in America, the government takes half of that. So you're roughly talking about 160K.
Right.
It's not going to change your life. So it's definitely not the monetary benefit.
Sure.
However, I always point out, the Oscars have no financial award associated with them. So if you win Best Actor, you get 0 money as far as I know. You get the statue, you get a goodie basket that's worth 20 grand or whatever, but you don't get a golden medal and you don't get $1 million potentially if you win it by yourself. So it can't only be about that. So it must be about the prestige. And who does the prestige redound to? Well, it goes mostly to the winners, but it also goes in huge amount to the people that supported the winners. In other words, the funding agencies.
Or like the universities or whatever that they're working at.
Yeah, the universities. And you can find that in the rankings of universities and funding agencies in the United States, NASA, or, universities like mine. They'll list, how many Nobel Prize winners are on the current teaching roster, how many people won the Nobel Prize after being at UC San Diego. And I have no problem with the people that won it. They don't select themselves. You're actually forbidden. The only rule I got when I nominated winners was I wasn't able to nominate myself. So that was very helpful in eliminating at least 1 person out of 7 billion people in the world. But at any rate, the primary beneficiary I claim is the Nobel Academy, because you probably can't name another science award or even close. You certainly can't name another peace award that comes anywhere close to the Nobel Peace Prize.
Right.
And it's similar in all the fields. So it's become extremely important to the national identity of Sweden and to their national academy. And I came to find that there's only about 300 or 400 people around the whole world. Most of them are men in Sweden that are in charge of giving away this prize every year. So like any monopoly, the Nobel Prize wants to protect and sustain its monopoly. So it does what it can to keep the prestige as high as possible, at least the perception of prestige as high as possible. So they have YouTube channels, they televise it, they're building a huge new expensive glitzy hall in Stockholm where they're going to award the prize, just like the Oscars. Mm-hmm. The Oscars are not, there's no God-given dictate that, so-and-so is best actress in a film. It's just these people suggested it. And now the Oscars grafters have a brand that they also have to burnish. And so I do believe that one of the greatest beneficiaries is the Nobel Prize institution itself.
Wow. Wow.
So let's talk current cosmological projects that are happening in your world. We know you have a lot of things going on, but you are currently co-leading 2 international projects that are searching for B modes. So let's start with an explanation of B modes and why electromagnetic radiation is so important to furthering our understanding of the universe.
Yeah. So what's interesting about astronomy is that it's very difficult to do a true experiment. In other words, we can't change the temperature of the sun and see how that affects the orbit of Mercury, or do another experiment where we look at if the universe had 10% more hydrogen, what would the status of a certain type of chemical abundance be like? So unlike every other field of science, there's no way to vary a given variable. Everything we get, we have to receive. It comes to us either in the form of light or now waves of gravity or perhaps meteorites, and that's it. There's very few other things. Particles and photons really are essentially the main source of messengers that collect and bring information to the Earth. So we have to be very judicious and efficient about collecting this very faint light and heat that comes from distant sources in the universe. We do have one advantage over, say, archaeologists, which is that we have a time machine at our disposal. So every telescope that sees light, or microwaves in my case, or infrared light, or et cetera, is actually peering back the way that things looked at some time in the past. It could be 8 minutes in the past when you look at the sun through a solar filter. It could be 1 million years in the past if you look at the Andromeda galaxy, or it could be 14 billion years if you look back to the beginning of time in the early universe. That's what we do. Now the question is, how does that tell us about what happened at the very beginning of time? Well, in our case, we're looking not only at light itself, which has been stretched and lengthened as the universe expanded and cooled off from this fiery hellscape that must have been present in the early universe. And we know that for a fact based on the amount of certain elements that we see in the universe. We know how hot the universe was in its earliest moments. But if you go very far back to that trillionth of a trillionth of a trillionth of a second after the initial singularity, if such a thing existed, we're not sure a singularity existed, then you come upon a time when the universe was so small that it is impossible for the force of gravity not to be present in what's called a quantum state. So most other forms of forces of nature, so light, electricity, magnetism, et cetera, have a theory called the quantum theory, which ascribes a certain probabilistic interpretation to the various things that you can observe. So the probability of observing a given particle depends on certain quantum properties known as a wave function. We are trying to probe the wave function of the universe shortly after it came into existence. And that wave function, in theory, contains and encrypts and encodes a lot of information about how the universe will evolve in the deep future. So the exact type of information that we're looking for is a form of a wave of gravity, which is the last and perhaps only force that may not be unified with the other forces of nature. There are four fundamental forces of nature: electricity, magnetism, and two different types of nuclear force, and then gravity. We don't know if gravity has a quantum form to it. That's never been discovered. If we can find it, it would be the so-called discovery of the theory of everything. Again, that's an open source of research that my colleagues and I are interested in. So the signal itself, we're looking sort of for the smoking gun that would indicate whether or not the universe began in this expansion known as inflation. And the smoking gun is predicted to be a background of radiation, but not in the form of light or microwaves even, but in the form of gravitational waves. And if they're present, they produce what are called B modes, which are a type of twisting, swirling form of polarization that I describe in the book, and why it's so important. So the logic is the following. If we detect these B modes, this swirling, twisting property of the cosmic microwave background light, then that will imply the universe had these waves of gravity at an extremely early point in its evolution. If that is true, then the universe must have undergone a period of expansion called inflation. And if inflation is true, it's almost unavoidable that one has encounters what's known as the
Yep.
multiverse, which means that there might be not just, eight, just as we have eight planets in our solar system and 100 billion stars in our galaxy, 100 billion galaxies in the observable universe. It might be that there's 100 billion, a trillion, a quadrillion, or an infinite number of universes in what's called the multiverse. So, and that has tremendous ramifications and ripple effects in all forms of science, including maybe extending into pure philosophy and metaphysics, and certainly into the realm of theology and the notions of the existence of God. So I think all these things are really fascinating things to think about. And it's amazing that technology can finally answer this question. Because we thought for thousands of years the universe was eternal and static. Then we realized it was changing. Now we're sort of unsure whether or not the universe had a single origin. And if so, what preceded it, if anything? And then if not, was there a cyclic nature to the universe? And did that evolve over
Are you talking
time?
about like
So these are
the multiple banks theory there, basically?
Yeah. So there's multiple universes you could have in space. And that's called the multiverse, where there are parallel universes, and there's multiple different ways to have parallel universes. You could have parallel universes in the same place in space. You could have parallel universes in different places of space. And then you could have cyclic universes where you cycle from a big bang to a big crunch to another big bang. And those types of models have been around for a long time, but now we're sort of able to not prove them, but perhaps more interestingly, falsify them and rule them out.
Exactly. And we are going to come back full circle to big crunch, big bounce, all those things. I just have to ask you though, like your field specifically, you guys work within some parameters of some numbers that just hurt the noodle straight up, right? Like when you guys are talking about just like the distance and like just like trillionth of a trillionth of a trillionth of a thing, like how the hell do you even wrap your head around these things? Like when I watch a ton of documentaries about the universe, and like looking at just like different ways that we could potentially get to different star systems in the future. And when we're starting to talk about light years and we talk about the distance and like how long it would actually take human beings to get to a different star system based on our current technology. And then if you apply a coefficient to where if we could get to 17% of the speed of light or whatever, it's like, these are still massive, massive numbers. Like, how the hell do you even begin to wrap your head around this stuff? Is it just like time and practice, or is there like a mechanic in your brain that you've been able to just like tap into and make sense of it? How does it work for you?
Well, it's interesting because if you actually think about it, I think it'll be very difficult to, from a fresh start every time thinking about something to then go into and try to unravel its deepest nature. But on the other hand, if you can make analogies between things that are more familiar, we talk about 4 dimensions of what's called space-time. Really, it's impossible for human beings even to really truly conceive of 3 dimensions. I mean, we see our eyes have retinas in the back, right? And those retinas are basically planar surfaces, 2-dimensional surfaces of cells, of rods, of cones. And those having 2 retinas and separated by a couple of inches allows our brain very cleverly to synthesize a sense of depth perception. But we're not actually seeing into the table in front of you, right? We're seeing kind of around it and how it diminishes with distance, and we interpret that as depth. But in reality, we're synthesizing a 3-dimensional image from 2 2-dimensional images. Now try to imagine synthesizing a 4-dimensional universe from 2 2-dimensional images is basically impossible. So what we do is we make analogies. We start with lower dimensions, simpler forms. We make things abstract. We translate and build mathematical models for the universe. And then we ask, are there any astronomical observations that can illuminate, no pun intended, the aspects of the model that we don't know? So there's always going to be parameters and inputs into the model. Say you believe the sun, it takes 8 minutes for light to travel from the Earth to the sun, or from the sun to the Earth. Well, that is predicated on some measurement of the speed of light, which you don't get that from some other law of physics. You have to measure that and put that into an equation which says distance equals rate times time. And so that is an input into your model. And then you look for deviations from that model, but you can never actually prove that model is correct because it's always possible for the model to have some features that are unobservable with your current level of precision or within the commensurate with the uncertainty of the known parameter. In that case, the speed of light has some uncertainty associated with it. So we make analogies. We don't like have super enormous brains. We make models of things. And then we explore the ramifications, assuming the models are true. And we, most of the time, are looking for departures from the model. In other words, it'd be much more interesting to find that distance isn't equal to rate times time than it is with, outside the realm of uncertainty associated, as I described earlier.
Wow.
Let's take a second and try to explore some of the origins of the universe and looking at the early infant stages of the earliest moments of the universe. So you're essentially looking back in time. If time itself is a singular flow, how long has the light that you're observing taken to travel to where we can observe it?
Yeah. So what we are doing when we look back in space, we're looking back in time. And the way that you can sort of convince yourself of that, if you weren't, you guys are pretty young, but if you think back to the Apollo moon landing when astronauts were on the moon 225,000 miles from Earth, they would say something on the moon and it would take about a second and a half for, Houston to communicate with them. And so the round trip was about 3 seconds in this communication. And that's because radio waves are a form of electromagnetic radiation. It has nothing to do with nuclear, fusion or anything like that. It's just what we call waves that travel at the speed of light. And this form of radiation that we're looking for potentially came at the very, earliest instant after the Big Bang. If you've ever thought about how the universe originated, it may have come along with it the beginning of time. In other words, the beginning of what we can observe may be the only instance of a creation of a universe that we can ever observe. And so far, and in that case, we could never look back before that period of time. We couldn't ask, well, what happened on the Tuesday before the Big Bang? It doesn't make sense. But there are models of the universe, so-called cyclic models or bouncing models or quasi-steady state models that produce universes that arise like phoenixes. I don't know what's the plural of phoenix, from the ashes of a previous universe. And so in that case, it may be possible to not only find evidence for another universe, but actually that pre-existed our universe, but in some sense have evidence for the state and physical nature of that universe. In other words, not just that it existed. It's like, your great-great-great-grandparent existed, but you don't know what he or she was like. But imagine you had like a book or a video or, something handed out through time. That would give you a lot more information, obviously be a lot more interesting to you. But just knowing that they existed would be very interesting as well, and how and where. So courtesy of the fact that the speed of light is extremely fast, but is the ultimate speed limit in the universe that you cannot exceed. When you look back in space or listen with a radio wave, the example of the Apollo astronauts, you're actually perceiving things not as they are instantaneously now, but when they were in that condition that they produced this signal that you're now detecting. So in the case of the cosmic microwave background radiation, this 3 Kelvin background that comes in all directions from all parts of the cosmos. That light is the oldest form of electromagnetic light that you could possibly see. And so if you can build a telescope that can see it, which means convert it into digital signals that you could then make pictures out of and then analyze the pictures, those signals can then tell you about the composition of the universe, about the age of the universe, about the size of the universe, and very curious things such as, what's called the curvature of the universe. Is it possible to shoot 2 laser beams from 2 laser guns held at your hips and have them eventually come into contact with one another, cross through each other, far, far away from Earth in the distant universe? That depends on what's known as the curvature of the universe. And so all these different properties and more we learn about using this most ancient form of light. And in particular, we're hoping we can learn more about the most ancient light, which could be this form of not light, but waves of gravity. So ancient radiation, this so-called cosmic gravitational wave background, which may come from all directions in space.
Man. like just trying to wrap my head around it, and it's it's so intense. So let's go back to earlier in our conversation before the break. We were like starting to talk about expansion of the universe, right? So I think what would be helpful is first for some of our listeners who maybe like aren't super versed in that concept, maybe just give us a loose explanation of what expansion is. What does that theory look like? And I think that's going to tee us up for my next question nicely.
Sure. So when we look out in the universe, we observe now with great certainty that there's more than just the Milky Way galaxy that we inhabit.
Sure.
So our solar system is a single star populated with 8 major planets and, perhaps millions of little tiny fragments, comets, planets, planetoids. And that's one of 100 billion stars in the Milky Way galaxy. When we look out in space, we see 100 billion other galaxies in the universe. So rough math gives you a population of about 100 billion squared stars in the observable universe. In other words, in the universe that has had enough time to send light and existence that they exist, these stars and galaxies, to our telescopes on Earth just now. Then if you want to really blow your mind, multiply by 10 or 1,000 for the number of planets that such systems might have. And you get numbers like, a trillion billion, possible planets in the observable universe. It's just truly astronomical numbers. Now, when you look at every single one of those galaxies, with a possible exception of about 12 out of the 100 billion galaxies that we can see, all 100 billion minus 12 are moving away from us. They're expanding away from us in the interpretation of space between us getting bigger. Now, what about the 12 that I mentioned? It's kind of like, well, you've got 30 teeth or so in your mouth, but you lose one, that's the one you're going to focus on, right? So everyone knows that. Well, why are those other 12 not expanding? Well, that's because they're so close to us and the Milky Way is massive enough, or they're massive enough that we'll be attracted to them and we'll share kind of a common fate where eventually our galaxy will collide and coalesce with these other galaxies.
Much like how we're going to collide with Andromeda in like a massive amount of years, but like that's basically what it's looking like, correct? Yeah.
Yeah. Keep paying your taxes on the loss out there, okay? Because that's going to be a couple trillion years potentially. So exactly. So now if that interpretation is correct, then in the future, things will be more diffuse and spread out. And we actually know that since the time of Hubble in 1929, the universe is expanding in this sense. And that brought about the natural corollary to that idea, which is that in the past, the universe was smaller. So yesterday, the universe was slightly smaller than it is today. A billion years ago, it was a lot smaller. And 13.8 billion years ago, it was really smaller. It was perhaps, 1,000 times smaller. And the question is, what if you go back to time equals 0? Would it not be an infinite amount smaller than our universe is now? In other words, wouldn't it be essentially a singularity? And that's an unknown question. In other words, we really don't know what happened in the universe until we get to its ripe old age of about 3 minutes after it came into existence. So it could have come into existence from the pre-existing universe that may have collapsed and crunched to form enough seed material for our universe to rise like that phoenix.
Yeah.
Or it could come from a singularity, which is sort of like a white hole, which is sort of a black hole in reverse, spewing out matter, energy in all directions and causing an expansion driven by this mysterious type of energy, which is acting like an anti-gravitational force causing things to expand.
Yeah.
So that's our interpretation. We're basically running back the movie that currently shows things getting farther apart and interpolating back to early times. They must have been a lot closer together.
Right. So you're just trying to Quentin Tarantino the thing to figure out what it all means, right?
So what implications, does the expansion of the universe have essentially for the fate of our universe itself? We've seen a lot of conflicting theories out there. You have Professor Brian Cox. He's explained how the universe is going to continue to expand when all of the stars die, essentially like the heat death of the universe itself, taking all life with them into the darkness. Another theory about Big Crunch or the Big Bounce, which basically sees the reverse effects of the Big Bang or some great contraction or the collapsing of the known universe that triggers another Big Bang scenario. So based on your research, what's your take on the expansion of our universe and what's to follow?
Right. So what's so interesting about the universe that we observe is that it is expanding. It is getting bigger as we look out in galaxies nearby. Our with absolute certainty are moving away from us, except for those 12 that I mentioned before, those misfits that are getting attracted to us. Now, if you think about how the universe could evolve, the different ways that it could evolve, theorists of cosmology are very creative. They can think about different alternatives that can avoid the problem that is causing this experience that we seem to see of the universe getting larger. What is so fascinating to us is that the fate of the universe in the deep future is determined by this substance called dark energy, which seems to pervade the universe in all regions that we can observe. And even though it's very tenuous, even though there's very little of it, right now on Earth, in our bodies, surrounding us, we know almost nothing about it. And yet, because of it, it's acting as if the universe is being inflated again. It's acting as if the universe is expanding. And not only is it expanding, so Hubble observed these galaxies moving away at a constant rate. But this dark energy substance, about which we know extremely little, is acting like a cosmic accelerator being floored. In other words, you hold your foot on the pedal at a constant position, you'll speed up to some maximum speed, but then you want to accelerate, you got to push it further down to the floor.
Sure.
The universe is not exactly expanding at the pedal to the metal, but in the very deep future, because of it being controlled by this dominant energy form called dark energy, the universe will continue to expand, and it will expand at an ever increasing rate, unless it may be that the universe has this weird feature that the dark energy can mysteriously decay and go away. And if that happens, it may be possible not only for the universe to stop accelerating, for us to avoid this frigid cold state that Brian Cox was talking about, the number 3 favorite Brian of my kids in terms of astronomers, which is very, very frustrating.
Where do you rank in that? I mean, obviously Dad's number 1, then you probably have Brian Green, then we got Brian Cox. Is that the breakdown?
Exactly.
Nice.
Yep.
Nailed it.
Thank God Neil deGrasse Tyson's name, if it was Brian, forget about it. So I'm wondering, if we have a universe that is so mysterious that we really don't know what this properties of this dominant form of energy is, dark energy. I'm wondering, how can we say with great certainty what will happen in the deep future? And if you're wondering along with me, it's because we really don't know. We can't say with certainty what Brian Cox has said. We can't say with certainty that the universe won't, recollapse on itself if this dark energy dissolves away and fades into energy of the ordinary kind, the form of energy that you're more familiar with, just ordinary energy which acts attractively in the universe instead of repulsive. So these are open questions that we hope that our experiment, this one called the Simons Observatory, which I'm the director of, we're hoping that project will shed light, again, no pun intended, on this most mysterious question about this medium, this material, this very, very mysterious force called dark energy that is seemingly driving the universe apart, and how that will potentially impact the longevity of our current observable universe.
So basically, how fast right now do we know is the universe expanding? Like, what is the rate at which the expansion is taking place?
It's funny that you say that, because a couple of months ago, or maybe a year or so ago, we wouldn't have really had any controversial aspect about answering that question. We would have said the universe is expanding, and it's expanding at a rate that depends on how far away something is from us. So something that's twice as far from us, as a galaxy that's twice as far away from Earth as a given as the Andromeda galaxy, would be expanding 2 times as fast as the Andromeda galaxy. And that was expressed in terms of what's called the Hubble constant, which expressed the expansion rate of the universe given by these very strange sounding units of 72 kilometers per second per megaparsec distance. So a galaxy that's 1 megaparsec away from us would be expanding at a rate of 72 kilometers per second. Right? So very fast, not as fast as the speed of light, but quite fast. Now, if a galaxy was twice that far, 2 megaparsecs away, a megaparsec's about 3 million light years. So a galaxy that's 6 million light years away would be expanding at a rate of 144 kilometers per second, et cetera, et cetera. until you get way, way out in the distance. And that distance would then have would lead to an implied expansion velocity equal to or greater than the speed of light. We won't get into that right now, but nowadays we're finding that 72 number is controversial. So 2 or 3 years ago, it really was accepted by all cosmologists, and now we're having controversial debates and whole meetings and conferences dedicated to why astronomers don't agree on that value, and in fact are so vehement in their disagreement that they have to have like whole workshops and huge papers written about why we're getting two different types of results for this very fundamental parameter in cosmology, which governs how fast things are expanding away from us.
So, out of curiosity, let's say that Big Crunch is what takes place after expansion. Okay, and so the universe collapses in on itself. And earlier you had made the comment that the speed of light is the fastest, like that's the speed limit of the universe, right? Nothing can go faster than the speed of light. Is it possible though that if dark matter decays, goes away, does that allow for like the breaking of the rules of physics? Insofar that the universe could collapse in on itself faster than the speed of light, or is it going to be a very similar rate of collapse as it was expansion? Like what does that collapse look like theoretically?
That's a very good question. So this is an open aspect of research, and it comes down slightly to the realm of like sociology of science. Right now, 100 years ago, if you worked on an expanding universe, even Einstein would say you're a crackpot and you're an idiot and you shouldn't be allowed to practice physics. In fact, he said that to the man who first presented a theory of an expanding universe based on Einstein's own laws of what's called general relativity.
Sure.
And he said, your math is good, but your physics is atrocious, he said to this guy Lemaitre, who is a Belgian Catholic priest, by the way, who had kind of really come up with evidence that the universe might have had a singular origin. And that was much to the chagrin of Einstein, who thought the universe was static, essentially, and it existed forever. Now, when the universe was discovered to be expanding, he could no longer maintain the universe was static because it wasn't staying put. It was changing with time. As Einstein then later refined his theory, he came up with this idea that this term that he had added to make the universe constant and static was essentially a blunder. He called it, apocryphally perhaps, his biggest blunder. Now, if we end up looking at the universe nowadays, we realize that it was a blunder to say it was a blunder because this same constant that Einstein added is none other than the dark energy that we see today, or at least it has the potential to be in this constant form of energy that doesn't change or dilute with time. And the universe seems to be producing, for every cubic meter that adds onto the universe's size, it produces a certain amount of dark energy that seems to be constant throughout the observable universe. So we know a great deal about it. We understand and appreciate how the effects of this thing will behave, but we don't know what it is. So it's kind of like what physicists used to call like the ether or something like that in the olden days. So most people accept there was a Big Bang. Almost every cosmologist finds it inescapable that there was a Big Bang. And yet there are physicists working on theories that suggest there wasn't just one Big Bang. In other words, you could have multiple, perhaps an infinite number of Big Bangs, such that on the average, the universe is sort of static because it just is behaving cyclically. So imagine like these, kind of, when you go to the disco, as I'm sure you do, all the time.
Every Thursday, yeah.
Yeah. And there's a strobe light flashing. When you look at something that's changing, if the strobe is synchronous with that rate of change of whatever you're looking at, it'll look static to you, even though it's moving. And so mechanics use that when they look at your timing belt in your car, et cetera. And universe is looked at every trillion years or so. Perhaps they would look static to an observer who had such patience, if you will. And so it's really fascinating to think about, but it's almost out of the mainstream of cosmology that people observe and think about these effects in order to really understand how the universe began. Really requires that you overthrow conventional wisdom. And that's where these people like Sir Roger Penrose or Professor Paul Steinhardt at Princeton and other people have conjectured scenarios where the universe could be actually cyclic on very long timescales. and they're very much out of the mainstream, but they're very much, more brilliant than I ever hoped to be. So I have to take them seriously. But as I said, we don't look to prove them right, because when you do that, you are susceptible to what's known as confirmation bias, that you may end up seeing what you want to see, even though it doesn't really exist.
Yeah, when you're a hammer,
And
everything's a nail, right?
exactly.
Right.
So in our case, we want to be very dispassionate and look for evidence of cyclic universes, but perhaps to rule them out may require an experiment exactly like the Simons Observatory.
So one last question before we jump into a few whimsical questions that I have prepared for you today, because, why the hell not? So like, just based on your data, your research, what you're currently seeing as the shape of the landscape that you're working in, are these questions like questions that can be answered within our lifetime, in your opinion? Or do you think that this is going to be a continuation of multiple generations working towards the same common goal? Like how close are we to really understanding the fabric of the cosmos, the nature of reality, the universe as a whole? Or like, what are your thoughts there?
Yeah. So there's a lot of different crises that cosmologists and physicists go through. And I always joke, maybe we need a good psychotherapist to help us with all of our neuroses. I don't know if you ever saw Annie Hall, but Woody Allen's character gets obsessed when he's a kid because the universe is expanding and eventually be apart. And then his mother says, well, Brooklyn's not expanding, so do your homework. Brooklyn's not expanding. And I feel that way too. There's kind of a practical aspect of what we do. And then there's a real ethereal, metaphysical aspect of what we do. And there are things that we may never know. And it's uncomfortable as a scientist, to think that there are mysteries, for which we will never provide an answer. On the other hand, it's also very pleasurable because it means that there's all these puzzles that are out there to solve. And I don't know if, when I was a kid, if I ever solved like a Rubik's Cube, which I think I did once, I try to do it again. And you're like, that's pointless. Like, why would you want to do something you've already done again? Like, it doesn't do anything for you. But actually it does, because every time you do it, you recapture a little bit of that taste of excitement of doing it the first time. And in our case, we have all these mysteries that could be solved or may never be solved for the first time. So, and one of those is perhaps the origin of the universe. Is it forever inscrutable? Is it hidden behind this firewall of ignorance owing to both its distance or perhaps its faintness in a certain sense? The universe, we think of the Big Bang as this extremely violent event, of which it was. But then you think of how much the universe has expanded and diluted and how little there is in the universe today. If I tell you that, if you go into the, deep intergalactic space and you have a box, like a size of a wardrobe box and that you might move from your house to house in, you might find one proton or maybe even half a proton inside that entire box, or one electron or inside that. And that's just incredibly minute. There's almost no way to comprehend how empty space is.
Yeah.
And how dilute it is, and how alone we may be. I mean, might be in a minority amongst my colleagues, and I think we're probably the only intelligent civilization that exists and may have ever existed. And we may only ever know of ourselves as the only intelligent species to have existed. Doesn't mean that there might not be life elsewhere right now, perhaps right underneath our noses. But on the other hand, signs of technological life may be impossible to ever gather, let alone information about another universe that is potentially completely unobservable and must be induced from other knowledge that we glean. So I personally find it exhilarating, but I know to other people it's incredibly depressing.
Sure. Well, and there's such a difference between microbial life and intelligent life too, right? So it's like, it's not an apples to apples comparison for sure. So, but no, thank you for walking me through that. Holy hell, man. I want to get you back on the show. I want to make sure that we're able to continue the conversation, because I have a billion other questions I want to ask you. I do have 3 whimsical questions I want to hit you with real quick.
Yeah.
What is your favorite celestial object, right? Are we looking at like pulsars, quasars? Like what's the weirdest or most intriguing or interesting thing that you've been able to see when you're observing the cosmos?
Well, for me, it'll always be the moon. And
the moon.
The moon, because that's really the first thing that kindled my interest as a scientist and led to the first bit of scientific research that I ever did back in the 80s, when I woke up one night and I saw this really bright light, and next to it was another kind of smaller but equally bright light. and I didn't know what it was. I thought it was a plane, but it never moved. And the moon was just so enticing. It was just fascinating to me. And I always wondered, as I'm sure you have, why is it that the moon always follows me wherever I go? And I later learned that was because I'm, the most important person who's ever lived. And no, I'm just kidding. The why that effect is true, owes to the distance and the size of the moon and the Earth. But I'd always wondered about that, and it wasn't until I was able to wait for a newspaper, those things printed on dead trees, to arrive. This is 1984 or so.
Sure.
That I realized, a week later almost, what I had seen was the moon and the planet Jupiter. And immediately after realizing that, I set about to get my first telescope and looked at Jupiter through the telescope and saw it had moons too. And I had unwittingly repeated this observation that my man who became my astronomical scientific hero, Galileo Galilei, discovered the same things. Now, I'm not comparing myself to him. He achieved some slighter degree of fame than I did. But as I describe in my book, my fascination with discovery and research and having to be patient and wait to understand these things. Now, I've seen many beautiful things through a telescope, but that first observation, those observations that I made with my eyes and with the telescope, really are what hooked me on becoming an astronomer and took me through the professional path that I'm on today. That's
amazing. And listen, I got to just be frank with you. Galileo, yes, big name, made some solid contributions to the scientific community and the field in general. But I will say, I appreciate the humility, but that dude was never on Lost Origins. I'm just calling a spade a spade.
Yeah, no, that's true. That's true. I mean, just like Einstein, the two of them are known for making great contributions, but also they had a lot of errors and blunders. I already mentioned Einstein's.
Sure.
Galileo had his share too, and I talk about it. And I say it's really unfortunate because, if Einstein hadn't made those blunders, he could have made a name for himself.
Sure. Okay, so second whimsical question, okay? Favorite space/sci-fi movie in existence?
Well, I am the co-director of the Arthur C. Clarke Center for Human Imagination at the University of California, San Diego, and you can search it on the web. We have our own podcast, and maybe someday we'll do a podcast, a hostage exchange, where we'll have you on the podcast. In our case, we study human imagination and how prescient Sir Arthur C. Clarke was, and it's a real inspiration to carry his vision of both science and fiction and writing from the 20th century to the 21st century. And so for me, it's 2001, A Space Odyssey. It's my favorite movie in the science fiction genre.
Very good. And your mention of a podcast hostage takeover, in last season we did one with Cliff Dunning from Earth Ancients, and it was super cool, and we would be so down to do that. So you just you tell us when and where, and we'll make it happen. Last whimsical question for you before we get into unpacking what it is you're currently working on, where people can connect with you. This one's the most serious of them all, though. Okay, so I hope you're sitting.
I am sitting.
Okay. Out of curiosity, which character from the Big Bang Theory do you relate with the most? If you have to pick one. It doesn't have to be one of the main characters, right? Like it could be Stewart, it could be anybody. But if you had to pick a cast member or a character from that series, who is it and why?
Well, I hate to disappoint you, but I don't think I've ever seen a full episode of The Big Bang Theory.
All right. Well, I will pen a strongly worded email, and I'll send that to you afterwards, just to express my disappointment. But it's okay. Yeah. So, okay. Before we go into how people can connect with you online, what you're working on, whatnot, I think it'd be cool if we have any younger listeners on the show who are trying to look at what they want to do with their life. They're very drawn to the origins of humanity. They're drawn to science. They're drawn to asking questions. And let's say that part of them is really, really attracted to the cosmos, the universe, and your field specifically. What advice do you have for that young budding mind as it relates to how and why they should continue to go down this path, ask these questions, and why astrophysics could potentially be a field that is warranted for them?
Yeah, well, for me, astrophysics connects all aspects of science into one, and it's unique in that respect, in that we can talk about the fundamental building blocks of matter, quarks, leptons, etc., We can talk about which are the smallest structures in the universe, and maybe strings, microscopic superstrings. And then we can talk about the entirety of the universe itself. So the smallest scales to the biggest scales. We can talk about the chemistry of the universe, how different elements were formed inside of stars or in the Big Bang itself. We can talk about biology. We can understand how life might have originated on Earth, and if it may exist on other planets. If it does exist on other planets, what types of signals might they send? We can study information theory. We can build telescopes. We can build technology. We can build theoretical models. So it's so all-encompassing. But to me, the most delightful thing is that all of those can then have ramifications in philosophy, perhaps in theology. And so it's the biggest possible subject you can study, with no offense to any of my colleagues' professions and their subfields and disciplines within physics or even within astronomy. It takes all sorts of astronomers to make the models and theories that we have in the universe. So for me, building telescopes gave me this connection from the smallest things to the biggest things, and really whet my appetite for research, for study. And I always say, for the young people out there, you should really get a telescope. You should get a telescope and get an app, $3 app. I'm sure there's millions of them out there that will tell you what things to look at. Now, when you look at them, you're not going to see this Hubble Space Telescope image, that looks almost three-dimensional and is just going to blow your mind. It's going to be a smudge. It's going to be a bright dot. It's going to be all the, very much a letdown, except when you realize that your eye is connected to the greatest minds in human history, stretching back to Galileo, all the way back to the ancient Greeks. And in so doing, your mind is part of this unfurling chain of scientists that stretch from the deep, deep past through you, my young listener out there, into the ever-increasing, unfurling future. And so for about $50 on an online store, you can, after you buy my book, you can buy a little telescope. And that telescope with an app will show you some really cool things. And it's a real golden age now where Elon Musk and Jeff Bezos and all these other people are putting, potentially manned space missions into space. If you want to be an astronaut, there's no better scholastic training that you can get than astronomy. And so I really do believe that it is one of the most wonderful sciences to be a part of, and it can be done quite cheaply. Try getting your own particle accelerator at Amazon. You won't be able to do it, and you won't be able to make those instantaneous, gratifying discoveries that you can with astronomy. You can see through a small telescope even more things than Galileo or Isaac Newton saw, and think of the contributions they made. Even from the middle of New York City, you can do it. You can see the moons of Jupiter, the rings of Saturn, every crater on the moon that Galileo could see. So it's really quite a wonderful time. And you couple that with all the free lectures that are available online on astronomy, it's a golden age to be a young person thinking about doing astronomy in their future.
That's amazing. And I think it's important to point out that even with light pollution in a city like New York, you can still see things through the telescope. You don't have to go to some desolate location to be able to turn your telescope towards the night sky and really just take it all in. You know what I mean?
That's absolutely right.
All right. So before we part ways, I know that your time is precious and I don't want to burgle any more of it. What are you currently working on? Is there another book in the works? How can people connect with you and your work online? Is there a website, social channels? Just kind of walk us through that real quick.
Yeah. So I'm on all the normal social channels. I'm Dr. Dr. Brian Keating on Twitter, Instagram, and YouTube. And I'm trying to put out a video a week or so on YouTube, short videos about the research or books that I'm reading, things I think people find interesting. And then I have a mailing list that I send out about 4 or 5 emails a year. And for those of you out there who are listening, if you sign up at briankeating.com, BRIAN, Keating, KEATING.com, I will select at random 3 winners will receive a genuine piece of space dust that's 4.3 billion years old.
Whoa.
And this is a meteorite from the ancient solar system, the pre-planetary solar system. which I've collected. These are small little samples, but this is some of the most ancient material you can get, and it plays a very vital role in my book. It's sort of the villain of my book in the form of this space dust signal, and you'll hopefully become endeared with this substance. And it's one of the few pieces of tangible material you can actually hold from the distant universe. So that's 3 random signers up, if that's a word, for my mailing list. And you can do that at briankeating.com. For your first name, just use your first name. For your last name, put Lost Origins.
There you go.
And I will send a genuine piece of space dust to your listeners, the 3 randomly selected listeners.
That's amazing. You guys know what to do. Hop on the website, sign up for the newsletter, throw Lost Origins in there, and man, get yourself some space dust. That's incredible. That's so cool. Thank you for doing that for our audience. I appreciate the hell out of that. So listen,
absolutely, this
conversation was so intriguing. I appreciate your time so much. I know that you're a busy guy. I also know that you're a family man, and so thank you for carving time out for us today. CK and I enjoyed the hell out of this conversation. We definitely have to get you back on the show in the future because, like I said earlier, I still have a billion questions. I will continue to add to that list.
Brian, this has been one of the coolest conversations. Thank you so much for spending time with us. We've looked forward to this for a while, and thank you for spending so much time digging so deep into stuff that's so heady.
Let's keep in touch, and we will definitely make that happen soon.
Absolutely. Let's not make it another billion years before we get together.
Damn straight. Well, thank you so much, Brian. We appreciate it.
Absolutely. My pleasure, Andrew.
Bye now.
Bye.